All right. So last week, after the visualization, I gave you guys a theoretical assignment to go and read through or just like assess some information about machine learning. Is there anybody who tried to read one or two things about machine learning? Be truthful.
I
Anybody?
did, sir. I did, sir.
Okay. Who else? Any other person?
I also did. I watched video.
Oh, okay.
I was not in class, but I've read some things about it sometimes ago.
Okay, so from those of you who have read or you've read something about or you watched video, what do you think machine learning is? Anybody? I mean, you are no right answer, no wrong. Just tell me and then we'll correct ourselves. Anybody?
I think it's used for predicting future values based on like training from previous data, something like that.
Okay. Any other person?
Okay, I
Machine
think it's
learning is a form of training an algorithm on how to identify data sets based on previous data available, probably supervised or unsupervised.
Okay, great. Any other person?
yeah, I think it's basically like training the data, like you teach the computer like based on past data. And then without being explicitly programmed, we expect the computer to make decision whenever the computer comes across similar data.
Great. Great. Any other person? Who else? Any other person? Okay. So you are all right, and there is an element of truth in what the three of you have said. And I noticed that you're all saying you're all making there's one thing that is common in the three of you, which is about a computer training data. And that's very correct. And Kudus also mentioned a word. He said, without being explicitly programmed. That word is very important. In the past, before the machine learning had actually been existing for a long time, but before this improvement, this great improvement in it because of technology, availability of powerful computers and data now, what programmers used to do is that they will define rules. For instance, let's say you want to build a model, like you're a programmer or you're a data scientist, you want to build a model to predict the price of houses, let's say in the mainland in Lagos. Mainland like Yaba, I don't know those areas very much again. Ikeja, all of those things. Suppose you want to, but you have access to some variables like the population in each area, the income level, the average income level of the people in each area, the average number of rooms a building has, average number of bedrooms, the facilities, that are in each area like that. So you have access to all those data, let's say for a data ranging from 5 years. And you want to, so they gave you all those information, the data. And so in the past, what programmer used to do is that they would define rules as, okay, come up with rules such that we call these rule-based methods, such that, okay, if an area has so number of population and the income level of the people in that area is this, and the average number of bedroom is this, the house price should be like this, the house price should be so amount. Those are rules made by humans. But over time, they realize that those rules, they are susceptible to errors because there are many rules to make. Just like you are a data scientist for a bank, you are working in a bank as a data scientist, and they want you to build a model to predict whether a customer we we actually get like subscribe for credit card. It is like that. So you have to define, maybe part of the information they have is marital status, whether that customer is married or not, male or female, that's sex, whether the person is on loan or things like that, or a model to predict whether a credit card should be approved, credit card approval. In fact, I think that's the first project you are going to do, or I can limit it to just a single project. So let's say you have those information, you are going to now design rules like, oh, if the customer is married and is earning, his income level is also amount, maybe maybe the income level is low, is not going to, we shouldn't approve it because it's going to actually default in that credit card. So coming up with those rules over time show that they are susceptible to errors, because programmers cannot cover all the rules, and use cases will also make the rules to not very well, because the case, you can't cover all cases. That's the point. So that's what makes machine learning now very useful, because machine learning is now the process of a machine or a computer, in fact, better put, an algorithm to predict an output using past experience without being explicitly programmed. Explicitly programmed then means that without you defining rules for the computer. We are allowing the computer, by computer I mean algorithms, we are allowing them to come up with rules themselves, to come up with decisions in the data as to whether a customer we subscribe to a credit card, or whether the housing price will be this amount or this amount or this amount. So you are not the one making the rules. All you are doing is feeding the data you have to the computer, to the algorithm. That's all you are doing. The algorithm is the one coming up with rules themselves. So that's the difference between what used to be and what we now do in machine learning. Okay, so, but machine learning is a subset of artificial intelligence. So if you are doing machine learning, you are actually doing AI too. Is a subset of artificial intelligence. And deep learning, which you are not going to do, is a subset of machine learning. Maybe if you wow me so much that you actually do very well in the project, maybe we'll give you a scholarship to take our master class for free. Maybe. But I'm not yet wowed, but maybe by the project. So under that, you will see deep learning. And you can read it on your own because you guys are smart. Okay? So, but for this, we'll focus on the machine learning. All right? So we've looked at what is machine learning. So, but machine learning can be divided into 3 types. Idris mentioned one thing. He said supervised or something like that. So that's machine learning can be divided into supervised, unsupervised, and reinforcement learning. 3 types: supervised, unsupervised, and reinforcement. How can you know that a problem you want to solve is a supervised learning problem or is unsupervised or reinforcement? Reinforcement is very scarce, and that's about robot navigation. Even a lot of people are doing, some electrical engineering guys are doing robotics without programming. That's not what we're talking about. We're talking of robots that are really, really programmed. Yeah. There is a particular robot, I'm going to get the name. That robot has been given US citizenship because the robot was programmed in such a way that you can interview the robot and you'll be talking as human. I'll find the name and I'll give you to check it on YouTube. You can at least watch a simple conversation between The robot, and the robot was so that he has been given US citizenship as a citizen to operate with people. So that's reinforcement learning. Designing games, that's reinforcement learning. But when we talk, but we are mainly going to focus on supervise for your class. And the supervise is divided into two. But what makes it even supervised is from the data that you have. In your data, like I said, the house prediction, housing price prediction. If you, and we're going to do that today if time permits, if your data has variables and especially the target, if there is an example of the output you want to predict in that data, like an example of price of previous housing, if you have it present in the data, then that is a supervised learning problem. Why? That housing price of the past data can teach the model, the algorithm, the computer on how to make prediction of future housing prices, because it's only going to be looking at rows that, okay, this for this particular data, for this particular observation, the housing, the number of house, the average number of room is 5, the income level is this, the population is this, and the price is this. Okay, it looks at another one. The housing price, the average number of room is this, the income level of this one is this, the public, and then looks at the price. So over time, it's going to see a pattern that, okay, maybe all area that have this average number of rooms, that have this population size, and that have this income level, have this housing price to be this. You know, those are the rules that I said humans were doing, but he's now going to be the one looking at multiple rows. That's why people say that for machine learning, that you need enough, like big data. It's not so much, but at least the data should be quite more. So after looking at multiple rows, it's going to come up with rules. Rules to classify the data, rules to make prediction. That's what it's doing. But that target example output that you have, for instance, the pricing of the previous houses, is what is actually helping it to make that prediction, to come up with those rules. So if that is there, we call it a supervised learning. And this do you have a question? Do you understand what I've said so far? Any questions over? Do you understand?
It's very clear, sir.
Great. So now we have two types. We have the regression. An example of regression is what I've been saying, like predicting housing price. Like once the goal is to predict numeric output, continuous values, stock price, housing price, price of a product, weather forecast, or if the goal is to predict continuous value, numeric values, then that's a regression problem. I'm taking time on this because if you are working as a data scientist and they give you a question that this is our goal, this is the business problem, you need to first figure out if it's a machine learning problem. And this is how you will know if it's a machine learning problem, like, oh, do we have data in the past for that can model that can answer this question? If the answer is yes, fine. That's good. That's one. Two is that is it going to automate repetitive tasks, like repetitive human tasks? If the answer is yes, okay. So that means it's a machine learning problem. Then you now need to ask, is it a regression problem or classification? By classification, it means the goal is to predict the categories of that output that you have in the data. For instance, if you want to build a model to predict whether a fraud has occurred or not, you can see fraud occurs or not. Or you want to build a model for an organization to predict whether the employees of that organization will leave, we attrite, we call that attrite, will leave or not. You have an example of the output of some employees that have left, but they have some attributes. maybe based on the number of years they have spent, maybe where they live, the housing distance, maybe the number of years they've stayed on a particular level without promotion. You have all those information, and you have an example of the output that attrite, yes, attrite, no. You have something like that. You may, if you want to build, so that's yes or no. No means the employee will not leave. Yes. So once the goal is to predict categories, or whether a patient will have a cancer or not, based on the symptoms, based on the variables, based on the variables in the data. Those are classification problem. Fraud detection, customer retention. Maybe the customers, some people call it customer churn. Maybe the customers of an organization will churn or not, will stop patronizing the organization. Those are categories. That's classification problem. Because you need to first ask yourself those questions. Is this problem a supervised learning or not? Now, if the data that you have does not have an example of that target, of that output that you will use the model to predict in the future, then that's unsupervised. That means there's nothing like a teacher, no output, no target to guide the model to design its rules. You are only feeding the features alone to the model. And the model, most of what we do there, we do what we call clustering. Like, okay, I don't know. I know Netflix is not that common in Nigeria. Do you know about Netflix?
Yes, sir.
Yes, sir.
Great.
Yes, sir.
Great. Or even in your email, do you observe that if you go to Google and you check some products, do you observe that in your email, they normally advertise those products?
Yes, even Facebook.
Exactly. So what is going there is unsupervised. Is we call recommender system. So, and clustering is looking at those products and it will be suggesting similar products to you. That's what we call clustering. That's unsupervised learning. Unsupervised, that's what they use. They use clustering algorithms so that algorithm is monitoring the search of each person. If you search for some products on whether some films on Netflix, you will just see that it will be suggesting some other films to you. If you check on Facebook some things, and you see that if you check some things on Google, it will be suggesting it to you on Facebook. They link all of this, and what is working underneath is what we call supervised learning. It's clustering similar products, similar to what you check, and suggesting them to you. Yeah? It will even tell you some customer view this, other customers view related items that other people view. That's what we call cluster. It cluster those things, but we will not get there for your class. But you can read more about them. And if you in the future you have questions on them, feel free to reach out to me via email or LinkedIn. Okay. Yeah. So that is that. I don't. Oh, sorry. Is this clear? What I've explained so far, is it clear?
Yes, sir.
All right.
Very clear, sir.
Yes, sir.
So now we've assumed that okay, we want to build a supervised learning. That's the problem that we want to solve. You don't just take the data and throw everything to the model. The reason is because every model is built for future use. Because in the present, we know the answer to the problem we have in terms of, the price. A real estate manager will look at this area and say, the pricing of this area of the houses which should be built, we are going to build in this area. They sell land, they look at, okay, this is the value. If they are not using models, they're actually using experience to come up with those prices. And you may think they are right. They are using, they will say they are experts. They may be right to an extent, but they cannot be 100% right because your experience will fail in some times. So instead of paying an expert to come a real estate expert to help us design rules as to the price of this virgin land of the housing that will be here. Do we have data of the previous lands like these in this particular area, or even not in this area? And then we look at it that maybe after 5 years, the land, grew to it became very, very big or very popular, and the price. Do you have all those? If you do, you can build a model to predict the price of the house of this house in the next 5 years. You can, if you have. So instead of relying on the experience, we want to rely on the data. That's the goal. So suppose we now have it, what you are going to do, because the goal of the model is to predict for future occurrences, we need to have something to simulate future data, but we don't have future data because you're in the present. So that's why you will always split your data into 2 or 3 sets. And that's what I call training set, validation set, and testing set. At worst, you should have 2, training and testing. But in the industry, the ideal way, you should have 3. And I will explain what it means. The training data is what you use to build the model. That's what you use to come up with the model. Okay? And then obviously at the first time you build it, this model will not be perfect. No. So, but you can improve the performance. So if you want to check how well the model is performing, you check that. If you have 3 sets, you will check the performance of that model on the validation set. So when you check the performance, there are some parameters that come with those models. You can adjust them. By the time you adjust them, that may improve the model. You can check, just be careful with my choice of words. It may improve it. From experience, it does, but not all the time, depending on the amount of data. So it may improve the model. So you do all of the adjustment, everything on the validation, you retrain it again, you adjust some of the parameters that are important, you check the performance again on the validation, you rebuild it again. Let's say you now got to a point, you are now okay, this model is predicting well 99% correctly. You are okay. You will now finally combine the training and the validation data together and rebuild the model with the parameters you've discovered and their values, and then finally test it once on the test data. A lot of people don't teach this aspect, but I have to tell you how it's been done in the industry. Let me tell you the consequence of not having 3 sets. Suppose you have the 2 sets. You build the model with the training. The model is not perfect, obviously. You are going to check the performance on the testing because you don't have validation set. You check the performance the first time. Oh, that's how you know the model is not doing well, because the model will always be high. We have good performance on the training because that's what you use to build it. So we don't rely on the training performance. We want to focus on data it hasn't seen before. That's why you are having validation and testing. So if you don't have validation, you are checking the performance on the testing. When you check that the first time, you saw that the model doesn't perform very well. You adjust the parameters, the values, and then you retrain it. You check the performance on the testing again the second time. How many times has the model seen the testing set now? 2, right?
Yes, sir. Yes, sir.
Then you adjust the parameter values again, just to make it. You kept on doing that until you are now okay. But let me tell you, the disadvantage of that is that in the end, that model will become perfect. Even on the test data, it will be very high. You will say, wow, that's what we want, we should be happy. But no, the model is only giving you because you have exposed it many times to the unseen data, to the test data. It has now finally understood the patterns in the testing. Let me give you a layman example. let's say I'm saying I want to give you 1 hour test on what we've done so far. You don't know the question, obviously. I've trained you before. So that's the training process. I've been training you, teaching you several topics. That's the training process. Now, to check whether you understand how you are performing, your performance before I declare you to the world, to Nigeria, that no, these are now data scientists, tested and proven. Before I do that, I want to give you 1 hour exam. Now, the 1 hour exam is tough. Let's say you all failed it the first time. I now created a correction session. I corrected you on what you should have done. This is where you make mistake. And I gave you back the same question next time, like just 3 days after. What do you think? Will your performance be the same as the first one?
No, it will be high.
Good. You still made some mistakes, but not as the first one. I corrected you again and gave you back the same question. You know, in the end, you may all get 100%, right?
Yes, sir.
Does it mean if I give you a fresh, new question on that same topic, does it mean you will get 100%?
No, sir.
No. You may, on a fresh, new one, you may not get 100%. So, but if I didn't give you fresh new one, I just say, oh, based on this one you've been doing, corrected, redo it, corrected, these guys, give them any question on data science, building the model and all of that, they'll get 100%. You know, that's overly optimistic. That's too expensive decision to make. If they now call you out there, let's test them. That may not be. And that would be like, what has happened? That's exactly the effect of having 2 sets. Tuning on the testing set, retraining the model, tuning again, adjusting the parameter. The model will become overly optimistic. But that model doesn't mean that if we give it fresh new data, that is going to perform very high like that. So the ideal way, and the project you are going to do, use 3 sets. Does it make sense?
Yes, it does, sir.
Yes, sir.
Yes.
Any questions so far? Are we good?
Yes, sir.
Okay, great. So let's look at everything together, like the life cycle. So the first thing, you are presented with data. You already know so you ask yourself, is it a regression or classification problem? Or the goal is to predict categories of the output. So we know it's a classification problem. Okay, let's say you want to use 2 sets, split it into training data and test data. But remember, I said the ideal is to use 3 sets. But let's say you want to use 2. So you split it into these 2. You will use the training data to train the model. That's after this training, you can see you train the model. So the algorithm is after it's been trained that it becomes a model. So the algorithm is what people call computer or the machine. So it's just an algorithm at that point. But once you're passing data to it and you train it, it produces a model. So that model, you will now test it on the test data by defining some metrics just to measure the performance of the model. One of the measure you do, for those of you in statistics, so maybe this one will make sense now. I know some of you might not have heard of it, but some of you have heard of what they tell you mean squared error. Has anybody heard that word before?
Yes, sir.
Yes, sir.
Just that they didn't tell you what it's doing. You are just memorizing formula at that time. But actually, it's actually a metrics to check the performance of the model on regression problem. So for classification, we're using accuracy. How accurate is the model? So it's checking how the mistakes our model is making. The mistakes the model is making That's what accuracy is doing, like checking how accurate is this model, what's the proportion of mistakes it's making. But if the goal is to predict continuous value, then what is checking that mistakes the model is making is that mean squared error. So it's just loss, it's mistake. So you want it to be very small, because mean squared error is just measuring the mistakes the model is making. And the smaller the mistake a model is making, then the better it is, right? So that mean squared error is just to measure the mistakes our model is making for regression problem. For classification problem, we use accuracy. As we go on, I will tell you other metrics that we use, but the most common one people use is the accuracy. I will tell you the function. We will do everything now and you will see. Does it make sense? Are we clear?
Yes, sir.
Yes, sir.
Okay, one final concept that we'll look at before we look at we'll start with linear regression, is the concept of overfitting, underfitting, and generalization. I don't know if anybody has heard about this term before.
Yeah, I have, sir.
Oh, so what can you say?
Overfitting is just like, I mean, let's say I went to Shodina bus stop and all of a sudden the conductors there snatched my bag and I just came back home and said, all conductors are thieves. I think I'm actually overfitting based on few amounts of data. That's like, I don't know, like training data too much that it will get used to one particular data and we start having generalization error in other ones. It won't be able to generalize well.
This guy I mean, he answered it perfectly well. Any other view from another person? Great. Okay, that's a good analogy and that's a good explanation, and I love that. So he used some terms I'm going to highlight. He used the word generalize. Let's keep that. And he used training the data too much. I'll correct that statement. But I understand what he's trying to say. And then, so what he's trying to say is that though the example he gave, yeah, we can relate it to it, though that's kind of extrapolation, but is similar to what he's trying to say. So overfitting just means that, and like he said, like it's just the process of training your model, building models such that that model predicts very well, like perform very well on the training data, but much worse on the test or validation data. Now, the question is, why does the model perform very well on the training data? And that's why if you see the rightmost here, I will tell you, so you can see that it's trying to make sure all red are separate from the green. Can you see my screen? Can you see that?
Yes, sir.
Yeah, so that's what we call overfitting. It's trying to be 100% accurate. It doesn't want to make a single mistake. It wants to be perfect in terms of separating, because machine learning is just about model that will separate the classes in the data. Like the classes, by classes, I mean categories of those of the output. So this model is trying to be 100% accurate. So what he's doing, so we say that kind of model overfits to the training data because it's too complex to the data. But when you give it new data, this model does not perform well. So that's what Kudus mean by it does not generalize well. So it's too weak to understand the pattern in the new data, but it's very complex on the data that we use to build the training data. Because while it's trying to be perfect, it also memorizes some noise, some things that are not useful in that training data, while it's trying to be perfect. You know, it's just like when you have exam, you like that course so much that you read the notes 5 times back to back. I've done it before while in Unilag. So you read it back to back, everything back to back. Does it mean the lecturer is going to bring questions on everything in the notes?
No.
No. So now, if in fact, great, there are some exams that you would have done in the past, and everybody, I believe you would have fallen into this category before, that you understand the notes, you read everything in the notes, and you understood. If they bring any question in the note, you answer it. But the professor brought a question not in the notes, though it's similar to a topic that is being taught, but it's totally different from any kind of examples in the note that you have done under that topic before. And you are looking at, you couldn't solve it. Has anybody experienced that before?
Yes, sir.
That's
Of course, many
exactly
times.
what we call overfitting. He memorizes, he understands all the patterns in the training data. He read all the topic, everything. But now when you give it new, but he even read what is not even necessary, but it's in the note. But when you give it new one, he couldn't generalize that. Okay, this topic I've read in the note is similar to this, the same concept in the note, I can use it. He was too weak to understand that. That's what we call overfitting. Is it clear?
Very clear, sir.
Yeah. Now, underfitting is you do not even read the notes. You don't read the notes, you don't understand the notes, you don't even understand those topics. And it's possible we would have everybody are falling into this category. You don't understand the note very well. You don't understand those topics. So even if they bring what is not in the notes and want something similar to it, you don't even understand what is in the notes. So there's no way you want to understand what is not in the notes that is similar to what is in the, that is similar to the topics that you know. So that's what we call that fitting. The model does not perform well. It performs worse on both the training and on the testing. So it doesn't even understand the patterns in the training data, and as a result, it's also weak to understand the patterns in new data. That's what we call underfitting. Is it clear?
Yes, sir.
Now,
Yes, sir.
generalization, that's the one we want. That the model perform well on the training and as well, much more on the testing. So this means you read the note very well, but you understand all those topics. You solve extra questions. You even understand that if they bring any topic, any question on that topic, similar, as far as it's on that topic, whether the question is in the note or not, you understand it. So you understand the note so much that when the lecturer brought a different question, but similar, but on the topics you have taught, you also perform very well on it. That's what we call that your model generalizes well. So it's performed very well on the training set and much more on the testing set. That's the good compromise. That's when we say your model generalizes well. Is it clear?
Very clear, sir.
So if I ask you to explain these 3 concepts, I hope you'll be able to explain even in a layman way, right?
Yes, sir.
All right, great. So this is where after this, we'll go to the notebook and we'll see how to do this in Python. And I'm sure you guys have seen this before. For the statistics guys among you, I know you guys are statistics guru. So we have done, you have been taught that there is different types of linear regression, like regression, linear regression, multiple regression. And linear regression is when your data has only a single variable, a single feature there, okay, and a single target. So in this case, the variable is the YouTube videos, and the sales is the target. So this was what Kudus was asking about in the LM plot for Seaborn, where I said that you could have a line of best fit. Now, so regression, remember we said is the goal is to predict numeric output, continuous value. So, but in most cases in the real world, you will never come across linear regression because almost every organization have data with many variables. So it will be like multiple linear regression where you have many variables. Now, the MSE that you were taught before, which I said is just a way to help you measure the, okay, I will take your question, but Dimeji, but wait. So where I said it helps you measure the mistakes the model is making for regression problem is gotten from here. The line that this plot is showing you is, that's your predicted target, your predicted output. That's what the model is predicting. The ... you are seeing is the actual output that we have in the data that I said it makes the model, it makes the problem a supervised learning, the output that you have. But the line that you are seeing here is this line is actually the predicted target. Are you with me? Hello?
Yes, sir. Yes, sir. Yes, sir.
Bruce, maybe
Yes, sir.
okay, maybe you should ask your question.
No, you've answered my question.
Oh, okay. Okay, you guys should give me just like few minutes. Let me, just a few minutes. Okay. So this line is the output. That's what the predicted one, the model is that is giving us. But the ... they are the observations, the original output that we have. Now, the difference between this, the difference between what that model is predicting, the line, and those original one are the mistakes the model is making. They are the mistakes that our model is actually making. That's the error. So the difference between them, the difference between the predicted and the original one is what we call error. And a way to measure the error that is making is what we call the MSE. That's why if you look at the formula your lecturer might have given you for mean squared error, it's something like this. Like they are summing the difference between your original one, the original target, which we call Y, and the predicted one, which we give it Y hat. And then the reason they square it is because so as to be positive. And then when they square everything, they divide everything by the total number of observation. And then because they say this is what we call mean squared error. Yeah. So that's what actually you are doing. It's just a difference between the original output and the predicted one. The square is just to make it positive because sometimes Y can be smaller to the predicted, so it won't be negative. You just square it, you take it, then you sum everything and take the average. That's what making mean squared error. That's all. That's exactly what you are doing under mean square error. So it's just a metric to measure the mistake the model, your machine learning model is making. So linear regression that you are doing in school is actually machine learning. It's just that they didn't say it, and they are not giving you the application. Any question? Are we good?
Yes, sir.
Good, sir.
Yes,
All right.
sir.
Okay. So maybe at this point, we might just have to go to our lab to see how all of these things are done and all of that. So let me have these. Let's see. All right, so let's see. So you have this introduction to machine learning in your Canvas dashboard. So everything I've explained, you will see it, that same thing I put there for you in case you want to read it from the notes. The loss function is the mistake I was talking about. That's the mistakes the model is making. Yeah. These are some popular regression, machine supervised learning. But for this, for your own class, we only look at linear regression and logistic. I don't know if we have time, I might just show you k-nearest neighbors. But the other ones is that you read about it, or if you happen to take any other class with us, then you might be exposed to the remaining one. So this is the formula you guys are used to in your school for regression. WX, W1, X1. Can you relate with that formula? W1, X1 plus, W2, X2 plus. Can you relate with it? Do you remember?
Yes, sir.
Okay, so what it actually means, the X that you are seeing, that's the data we have. Those are the variables in the data that we are going to supply to those are the variables, okay? Now, when you say machine learning, what the model is actually learning is the W, the coefficient. Those are the coefficients of the variables. That's what the model, we did not supply the coefficient to the model. All we supply to the model is the data, these X's, X1, X2. X1 for housing price can stand for income level of the people. X2 can stand for average number of rooms. S3 can stand for the population of that area, things like that. So those are the X's. We didn't supply the coefficient. So what the model is now coming up with is trying to come up with the appropriate value for the coefficient that will help it predict this Y. This Y hat is the predicted output. That's all that W is coming. Now, what leads to overfitting is when some W's, some of these coefficients are very high compared to others. So they will be making the model too complex. Remember, we've not talked about how to solve the problem of overfitting. We just talked about what they are. In next class, we're going to look at how to address the problem. But what leads to them are these W's you are seeing, those coefficients. They may be high for some because the model is the one trying to come up with them. So they may be high. So for those ones that are very high, they will make the model very complex. So when we want to talk about how to address it, then how to address the overfitting, then I will relate back to this formula. Are we together? So let's look
Together, sir.
at how regression can be done. Instead of going through this note and all of that, let me see, on your dashboard, do you have, let's see, your dashboard, let's see, if you have data on regression, do you have for machine learning? Yeah, you have regression data. So you can download it. This is the note I'm actually using now. You can download it, and you can download this regression data and extract it. So I'm going to use some of the data in there. Let me see. I'm not sure if I have uploaded it. Let's see. Okay, so I don't have it here. Let me quickly upload it. So you can download it and upload it too. I guess at some point I've downloaded it. So let me see. Reg data. Okay. Great. So I can upload it too to my Anaconda since I want to use the two. So I'm going to use one and you can play around with it too. Okay, you can play around with it too. So it's for regression, USA housing, and then the housing data. The housing data is actually boosting data. Okay, so back to our regression stuff. So I'm not going to follow these notes and all of that. So the library we're going to be using, just like for manipulating data, we were using pandas. The library, the worldwide library for machine learning is scikit-learn. Scikit-learn, and it comes pre-installed. It comes pre-installed with your Anaconda scikit-learn, okay? And it's popularly known as sklearn, okay? sklearn. So that's the library we're going to be using, okay? So in this library, there are different modules to do different tasks. There are modules there to help us split the data that we're going to see. That's the model selection module. There are modules to help us pre-process the data in case we want to scale the data, we want to normalize it. Like by normalizing, I mean you want to bring them to similar range. Because remember I showed you that if some variables have high coefficient, it's going to make the model complex. So suppose you want to make sure the models are in similar range or things like that. So there is a pre-processing module in sklearn that will help us. And when we want to check the accuracy, we're also going to call on functions. So everything we're going to be doing is from this package. If your Anaconda doesn't come installed with it, then you can install it by using pip install scikit-learn, but I'm sure it's there. Pip install scikit-learn. So if you want to install any package in your Jupyter notebook, since you are using Python 3, you can use pip install, then you put the package name, things like that. So I'm going to comment it. If you want to do that, you can do that. Okay. So now let me bring in the data, and then let me use one of the housing data. Let's start from the data and let's end by building a model. It's going to be a very simple model just to show you how this thing is being done. So remember to do that, we import pandas as PD because that's what you use to bring in data into your Jupyter notebook. Are you following me?
Yes, sir, we're following.
Yes, sir.
Good. So let me call this data house because it's about housing data. Okay, the URL, let me see. The URL is, because I have the data inside my Anaconda, I don't need to put all the path from my desktop. I can just look at the data is actually in the data folder here, and it's called housing. You can see as soon as I press tab, it loads it. So I can pass it to pd.read_csv. You already know how to do this one. I'll pass in the URL. Remember, if it's from your desktop and you are using, if the link is from your desktop and you are using Windows, remember to put R there to stand for raw string. Okay, so if I run this, so I have the data, let's check it. House is a very small data, just for experimenting. So you can see the data. So it's a very small data. Let me check the shape here for you to see. It's very small. I'm not sure. It should be about 500. rows. So it's a very small data. So these are the features or the variables. So when I when I talk about features or variables, I'm talking about these column names. Now, but the last column in this case is not always the last column, but for this one, the last column is the target I was talking about. This MEDV stands for the median housing price. So it's not always the last column, but you will always know. You will always know the target. You will always be told, because if you are not, if it's a supervised line, you need to know the target wave. So you will know. They will tell you, whoever is giving you the data. So in this case is the median, this is the median housing price, the Y. This is our Y. All of these ones can be our X1, X2, X3, X4, S5, like that, up to whatever X is in. So those are the X's. All the rows are the entries of those X's. This is our Y. So I want you to be related to this equation. We don't know the W's, the coefficient. And that's what the model want to learn. The linear regression model want to learn the appropriate coefficient for each of these variables, each of these X's. Okay? All right. So you need to check. Remember, you need to explore the data. You need to check if it has missing values and all of that. But I will assume you've done all of those things. I will assume if the data has missing value, you fill the missing values and all of that. The data, so you fill the missing values, you've visualized to check, you know, the relationship between those variables. You've done plotting, because if you are going to do project for me, you're not just going to get data and build model. No, you're going to do a lot of exploration, do data like your house.describe to describe the data, things like that. And then you're going to do a lot of, so you are going to tell me about the minimum, the mean of each of these variables. You're also going to talk about you visualize and take them 2 by 2, visualize them, or take each variable and check the relationship with the target using scatter plot for 2 quantitative variables. So you will do all of that, you will explain. That's a project. You are going to do that actually, and you will submit in everything in your Jupyter notebook. I believe you all know how to create notes like this in Jupyter Notes, in Jupyter Notebook. Do you?
Yes, sir.
Great. So it's just turning it to Markdown. You can see you do it from code. Just you can use any of the notes that I have there to as your reference. Okay. So and then you do. So suppose you've done all of that. You can even check correlation here. That correlation you were taught in school, you can do it here. Do correlation, that's .core. And I want to do correlation of all of the variables against the target variable. So I can pass MEDV. So if I do that, it will give me the correlation of each variable to the target, the median housing price. So if I do that, you can see some are negative correlation. If you remember your statistics, correlation is from -1 to 1. -1 means negative correlation, perfectly negative correlation. +1 means perfect positive correlation, meaning they are very correlated but positive. Positive is the one you are seeing in the scalar plot that we did that time, that as X increases, Y increases. Negative correlation means as X increases, Y decreases, things like that. So, so you can see some of these, the age of the house is about 38 correlation, but negative correlation with the meaning the older the house, the older the house, the smaller the housing price, that because it's negative. Obviously, you expect new house to be much more expensive than old house. So you can do all of those ones. So suppose you are now ready to build a model. You've done everything you want to build a model as the last thing. Let me put all the steps that we are going to go through. The first step is to select the features. We call it feature selection method, step. Select all the features. By features, I mean the variables and the targets that you are going to use to build the model. After that, split the data, that's the features and the target, into, I will show you 3 steps, but for today, I will only use 2 steps. Okay, 2 sets, I mean. But today, I will show you 2 sets because the data is small. And then we'll scale the data because we want to bring them to similar range. And then when we scale it, we'll train the model. And finally, we'll check the performance. For today, we're only going to use the accuracy. But next class, I'm going to show you another metric. Check the performance of the model using accuracy. But as I will show you other stuff using precision and recall. But today is only accuracy. You can check out this one too. So these are all the steps we are going to be doing. Are we good?
Good, sir.
All right. So first, let's select the features and the targets. I'm calling it features, but you can use any variable name. So we'll call on the data. So suppose I need all the features, I'll accept the target now. Since target is the Y, let's just drop the target. So we'll do .drop. Another drop, we need to pass in the data. And by default, the axis is 0, meaning drop the rows. But the variable we want to drop is a column, it's not a row. So we have to change axis to 1. So passing the variable we want to drop, MEDV, and we'll set axis to 1. If you run this and check features, you will see that you have everything except the target. You can see. So these are the features. The target is no longer there. I can convert it. Did I teach NumPy? No.
No, sir.
Okay. So because I didn't teach it, I've not taught it, I will not convert this to NumPy array. But if I want to, it's just to do dot values. I'll convert it to a NumPy array. So select the target. The target is the MEDV, right? So we select that. So now we've accomplished this first step. Select the features, the variables to train the model, and our Y, the target. So once we run that, we have it, and you can inspect it. You can inspect the target. You can see that's your Y column, this 24, 21.6, all of that. That's what you are seeing here. So we've done that first step. The next step is to do what? Split the data into 3 sets. But I said I will use 2 sets for now. 3 sets of training, validation, and testing. But I will do just training and whether validation or testing. It's the same step. You just have to do this. This step I'm going to show you. You just have to do it twice if you're using 3 sets. Okay, so split the data. So there is a module from scikit-learn. From scikit-learn model selection. And see, as I'm typing it, I just press tab. It will show me. From scikit-learn model selection, import, space, and press tab. So there is a model, there is a function called train test split. It helps you split the data into the training set and into the test set. And it does this randomly. You randomly select the rows from your data and assign that as the training and the remaining as the testing. By default, it uses 75% for training, 25% for testing. But you can adjust it. You can adjust it if you like. If you want 70, 30, 80, 20, you can adjust it. Okay? So this train test split, so is a function. What do we want to split? We want to split these features and want to split the target. So if you want to take, let's say we want to use 70-30, then there is an argument called test size. I will just say I want 30%, 0.3. That means use 70% for training, 30 for testing. But let's use the default of 75-25. The last argument I will spend is the seed. A seed is just like, it doesn't contribute anything to build the model. It's just because this function perform these things, splitting randomly. For reproducibility, that's why I'm setting seed. Seed is just to ensure that every time I run this function, it should pick exact same rows of data you have picked before. Because if you don't, and if maybe the first time I run it, I build a model. If I don't set the seed, if I run it again, it's going to pick different rows. And that means the first model I picked is going to be adjusted if I rerun, if I use this new rows that is being picked to build the model again. So we always set seed to ensure that the same rows it picked the first time. I just use 0. You don't have to use 0. Just put a number there. Every time I rerun it with that same number, it's going to pick exact same rows I used before. So that way I have the same model I have built before. So we want to split these features into, let's call it X-train and X-test. And I want to split the target into Y-train and Y-test. Is this step clear?
Very clear, sir.
Yes, sir.
Okay, so we have accomplished the second step. And let's run it and check how many are in each one. So let's check X-train. Let's check the shape. Let's check X-test. Let's check the shape. Remember, shape is for dimension. You can see. So it has actually divided the 506 now. So it's going to use 75% of that 506 is this. Is it 506 or 504? 506. Okay. So 75% of it is actually diesel. So it's using 379 to 379 rows is going to use as our training set, and the remaining 127 is going to use as our test set. So it's a very small data. Although there is a method to use if your data is very small like this, you can investigate that. It's called cross-validation. But I may talk about it if it's necessary. So, okay, so this is the data we want to use now. So the next step is to scale the data. Why? Why do you want to scale it? Look at, before we split it, see the range. One data has one variable, CRM, has a minimum of 0.006, a maximum of 88. But another one has a minimum of 2.9 to 100. That's even similar. Look at another one. Tax has a minimum of 187 to 711. That's different. That's a little bit high. Look at another one. So some of these, so since these variables does not have similar range, this one is even good. It's not too different like that, but at least a little bit. You want to bring them to similar range so that no variable dominates your model. So to do that, we'll go to the scikit-learn pre-processing and import. There are two of them I can talk about. There's one called standard scalar. But I will actually talk about the mean mass scalar. Now the standard scalar.
Hello, sir.
Yeah, go ahead.
What you want to do now is to scale the data, right?
Yes.
Okay.
So the standard scalar is similar to what statistics students have been introduced to as I'm trying to remember the word they normally use in school, like standard
Deviation.
Is
it deviation?
No, it's not standard deviation. You know your Z-score. You guys normally have
Standard error.
Yes,
Standard
code.
error.
this score. You guys have one book like that that you used to check. What's the name?
Difficult.
What forgot table?
A 4-figure table. So thank you, Jerry. So it's just it used to. If you go to the you know, you have uniform distribution. You have
Normal
normal.
distribution.
God bless you. Normal
Poison
distribution. When you go to the normal distribution, you see z-score and all of that. So that's actually what standard scalar is doing. So z-score standard scalar is going to transform all these variables you are seeing here, each of them is going to make sure that they all have a mean of 0 and a standard deviation of 1. That's what z-score is doing. If you ask you know, it's just that you guys do this thing manually, that they can give you a question and then they ask you to, what is the probability of this, and then, but you know, it's from a normal distribution. You will now do z minus this, the mean, divide by the standard deviation. You're actually converting it to have a mean of 0 and a standard deviation of 1. That's what we call standard scalar. So, but that's what this standard scalar is doing. It's going to adjust all the variables to have a mean of 0 and standard deviation of 1. But if you use mean mass scalar, it's going to adjust all the variables to have a range of, to be within a range of 0 and 1. Yeah, that's all it's doing. So the formula it's using is not a very big something. Suppose all our variables are x1, x2, and the rest. So these are the variables up to xn. You know, each of them are this CRM that I showed you. What it's going to do is going to first calculate the minimum of each variable. It's going to calculate the minimum. That's why we call it min max. It's going to calculate the minimum. It's also going to calculate the maximum. Then from each variable, let's say from x1, the first row in x1 is going to take, let's say this is row 1, this is row 1, this is row 2. So let me just do for row 1, the same is for every row. So for row 1, it's going to take the value that you have there, the value of that x1, is going to subtract the minimum from it. The minimum is just calculated from that column and then divided by the difference between the maximum and minimum. That's all it's doing. So that's what mean mass scalar is doing. That's the mathematics on that. So it's doing the value of that row value minus the minimum of that column divided by the difference between the maximum and minimum. So when it does that, that value will be between 0 and 1. It does the same thing for x2. It does the same thing for all of the variables there. That's like doing this minimum and maximum. Yes, your question.
My question is on these feature selection targets. Is it that you have to drop a particular feature to make it a target or what?
This right?
Yes.
Well, if you don't need all the variables in your data, then you might manually select the variables you need as your features using the log or iLog that we've talked about before.
Okay.
But because I need all the variables and I know it's only this guy that I don't need because it's the target, that's why I just simply drop it to save me the stress. Do you understand?
Yes, sir.
Does it make sense?
Yes, sir. Yes, sir.
All right. Okay. So do you guys understand what mean mass scalar and standard scalar now?
Yes, sir.
Yes, sir.
Okay, great. So let's see how to use it. So the first thing, create an instance of it. Create an instance of, I know I didn't teach classes in Python. If we finish and you want to take some Java and you have some, maybe you have tested it, you don't really understand classes and objects, you want to understand, then you don't worry, you can tell me, I'll teach it. It's a very simple stuff, but it's very, very important concept. But I didn't teach it because I don't want to be too deep to scare people away. So create an instance of the scalar. So let's call it scalar. And so I'm using the mean mass. You can try out the standard scalar. They perform very equally well. So to scale it now, so I will use this scalar now to scale the data. So let's call it X-train XTD or X-train scaled, just to make it different from the X-train, so that we have access to the original X-train. Okay, so we have, so I'm going to call my scalar and I'll do fit transform and I'll pass in my X-train. I will explain this in a minute, and then we'll do the X test scaled and call in the scalar dot transform on the S test. So you might be wondering, what is fit and transform doing? Then why fit and transform on the training and just transform on the test? So this is it. When you call the fit without the transform, because I can do this one after the other, I can first fit and then next row I transform alone. But to do it together, you are calling fit underscore transform. When you call fit, it will only calculate the minimum and maximum that I showed you. It's not going to use it to turn that row to that variable to have value between 0 and 1. No, it will just calculate it, final. It's not going to store it, it's just going to calculate it in case you change your mind that you want to use it. But if you now do transform, this will now take that minimum and the maximum that you just that you just calculated to transform each row, each variable, I mean. Any question on that?
No question, sir.
Okay, good. Now, so why didn't we do that for test sets? Anybody, do you know why? Why do we only call transform?
Because it has
Because
already calculated this value before. So we're just transforming it on all the other variables.
God bless you. That's very right. Yeah. Because if I call fit transform again on this, it won't give me error, but I've calculated different minimum and different maximum. So my data will not be identical again. So if I want to now check performance, it might be giving me error.
It's different.
Yeah, it will be different because the data is not similar. It might be giving me error now because the data are no longer similar, or the accuracy will be very, very low. So you only calculate it on the training, and on the validation or testing, you only transform it with what you have calculated here. That's all. So let's do this step. Then we are in we're almost there, the training the model. Okay? Are we good up to this point?
Yes, sir. I just
Yes, sir.
want to confirm something, sir.
Yeah, go ahead.
So the first thing this is under the scaling, under scaling the data. The first thing we did was to train the data. Then we now the next line there is validating the data.
Sorry, can you repeat that?
Under the scaling the data that you just explained now, the one that you just explained. This first line of code is to train the data, and the second one is to validate the data.
Which one? Is it?
X test. X train is to train the data. X test is to validate the data.
Yes. Mhm.
Okay.
Yeah. Any other question? Okay, good. So we are ready to train the model now. So to train it is very simple, but which model do we want to train? Which model are we talking about today?
regression model.
Linear regression. So the linear regression, if you remember what you were taught, if you have done statistical before, there is a linear model. So linear regression is inside the linear model. So we do from scikit-learn, sklearn, linear model. Import. Let me show you the step. There are many there, but we only go for the linear regression. Okay, so create an instance of it like we've been doing. Let me call it LR, linear regression. And then to train it, you just call this your instance, this LR dot fit. When you call dot fit, you are training the model. So you have to pass in the data. Let's pass in the scaled data. And then Y train, the target. That's all. This line alone we train the model. So you can see you are only training the model on the training data. The test data here is just to check the performance of the model. So if we run this now, the model has been trained. Yeah, very fast. So to now check the performance, so that's the final, check the performance of the model. So check performance. So let me, to check it is just to do lr.score. So score will give us the accuracy. For regression, the accuracy is the same thing as the mean squared error. Yes, but for classification problem, the score will give you the accuracy, is the same thing. Okay, so if you want to check it on the training set, we'll do X train, the data we use to build it. Oh, sorry, Y train. So, but to beautify it, let's to make it better, let's do print. So let's call this train accuracy. Let's give it where it's going to put the value, and let me approximate it to 4 decimal place. And then we'll do dot format just to format the answer, the result. So, and then I close out the bracket, that's all. So all this one is just to, everything from here to here is just to make it cleaner. The main code is this, lr.score, and passing your X train, scale, and Y train, that's all. So let me copy this and check the performance on the S test too. Remember I said normally on your project, you should use 3 sets. I will show you next class, just quickly show you how to create 3 sets, training, validation, and testing, that's all. It's just a single line. It's just this line we are repeating, that's all. Okay, so, but let me check this guy to test accuracy, and then we put S test, and then we'll change this one to Y test. Okay, do you see that? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So now this is telling us the training accuracy, the performance is 76.9 or approximately 77. On the testing, this is about 63.5. This is saying 70, about 77% of, no, let's focus on the tests. About 63% of the time, or approximately 64% of the time, this model will correctly predict the housing price. However, we can't quickly jump to that conclusion. Based on this accuracy of the training and testing, what do you think is going on? Does this model overfit? Does it generalize well? Does it underfit? Back to the concept we did, yes?
It's overfitting.
Why? Why?
Because the accuracy on the training data is higher than on the test data.
Okay, so it does not underfit, right?
No.
Okay, any other person could do?
It's generalizing, sir, because I'm looking at the data.
Okay.
There is no quite large difference, probably something around 0.13 something difference between the train accuracy and the test accuracy. So it seems to be very close to it, with the fact that we trained with 75% data sets and we are testing with 25% data sets.
Okay. So this is what normally happens when you are working in a group of projects in an industry. Opinions, and you have to back up. He backed up his own opinion. Shown to back up his own opinion. Any other person? Vera, say something. You are not talking. You are too quiet.
side because I'm not really okay right now.
You're not okay. What happened? Are you not feeling fine?
No,
Oh, sorry.
thank you.
Dimeji. Okay. Hmm. So Dimeji, what do you think? Is this the accuracy we got here? Does it show any? Does this model underfit or overfit, or it generalizes well? I think Idris, you are the one that said it generalizes well, right?
Yes, sir.
Okay. So Dimeji, what do you think? Shehu said this model overfits. Idris said no, it generalizes well, and he gave his own reason. What do you think?
Uh,
Based on this accuracy that you have.
Based on this accuracy, it's on the feet. Based on the, I'm coming. I'm just coming in. Something is.
Okay, so Kudu, what do you think? Does this overfit or underfit or generalizes well based on this accuracy? Are you there? I think Kudus is not there. Okay. Well,
Overfit, sir.
overfits.
Yes, sir.
Why?
Because the accuracy on the training data is more, though not the difference is not that much, but it's more than the accuracy on the test data.
Okay. Now, both parties are right. It depends on how you are looking at it. If you look at it that, oh, the accuracy on the training is higher than test, you can conclude that it overfit, and you are not wrong. However, if we look at it from the aspect Idris was looking at it, that this data is not large, it's just 379. And normally the training should be higher than testing, because the testing, you are not training it, you are only using the model train to check how it will perform on this new data. But the data is not large. The data is just 379. And then you are now, so given 379 rows, this model giving you about 64% is not that bad. Okay, it's not that bad. So, however, if you say it, so if you even tell me it's underfit, I will still not argue, because, well, if the data is larger and you are getting this kind of accuracy, I would say the model underfit, because that means 76% is not enough, it's not good enough. But for this small amount of data, I'm going to stay in the middle, that, well, we can say it overfit, and we can say, but I won't say it generalize well, because if it generalizes well, you want the test accuracy to actually be, if it is not higher than the training, it should be approximately equal to the training. So that's when you say the model generalize well. Idris, do you get that?
Yes, sir.
So one other model that can help us do that can help us improve it. When we want to talk about lean overfitting, I will talk on two models called lasso regression and ridge, maybe next class. But that's how to check the accuracy and all of that. So you can see, so I believe at least by today, at the end of today, we have been able to see that, okay, given a data, after we've explored it, visualized it, if the goal is to build a machine learning model, you can take that data you can build a model, like at least this linear regression model on it, right?
Yes, sir.
All right, so that's all we've done. So you can now practice that on the other data, the USA housing data is in the reg data. And that's why I gave this instruction there. Just, there's nothing much. Do all the exploration and visualization, but at the end, select the features and target like I gave, split the data into training and test, scale the data, build a linear regression model on it. This regularize, you may not be able to solve that now, except you have read something about it, but I will deal with it next class by God's grace. And by that same next slide, we're going to do logistic regression, because after that, we need to move to SQL and we're going to really do some SQL, manipulations and all of that, those queries and all of that. And then in the end, integrate it with Python. So our class may not be more than 4 classes again. Yeah. We're gradually getting to the end. After next class, I'm going to open up the project. The project is actually there, but I may change it. But I'm going to open up the project after next class so that I can start working on it. Any question before we end today's class?